Hi everyone, thank you for your interest in this presentation. Here we will talk about how you can improve your oil flushing for a clean system. And when we say system, we mean a lubrication system or a hydraulic system.
Here you're going to learn why the oil flushing is important and what's the rationale to do an oil flushing and 12 recommendations to improve your high-speed oil flushing. In the industry, especially the gas and oil and power generation, we want to keep our machinery working as long as possible, and on the other hand, reduce the time and cost related with maintenance. Frequently, premature failure is related with wearing and other issues related in some way or the other with the lubrication system. The performance of the lubrication system is related with the high velocity oil flushing during the commissioning. A poor high velocity oil flushing will compromise the operation time of the machine. This does not mean that the machine will going to fail immediately. We are talking about premature failures that are measured in years after the initial startup, but shorter than the average recommended time between maintenance.
Lubrication films are microscopic, and when we say microscopic, we mean like, for example, this shaft, the clearance will be 9 micrometers, but the dynamic clearance, the film that is built when it's rotating and lubricated by oil, is only 1 micrometer. The lubrication films have different thickness, but here in this example we can see that the lubrication film in a journal bearing is somewhere between 125 and 0.5 microns. And in this slide we can compare and see that the sand particle is not only abrasive but also can break the lubrication film. A human hair and a rust particle are also a threat for the lubrication film. I will give you more examples about the thickness of the lubrication films. In a piston pump, the piston film is somewhere between 5 and 40 microns. And in the same pump, at the cylinder, the lubrication film is only 0.5 to 5 microns. Now, in the ball bearings that are so common, the thickness of the lubricating oil is only somewhere between 0.1 and 0.7 microns. But now, look at this, the mechanical seals that are used everywhere, pumps, agitators, compressors. The thickness of the oil between phases is somewhere between 0.3 and 1.6 microns, and between the seal and the shaft the oil is only 0.05 to 0.5 microns. That is why it's so important to clean the plants for cooling or lubrication the seals. In conclusions, particles, especially microscopic particles, impair lubrication films in a hydraulic or lubrication system. For this reason, systems needs to be cleaned. The purpose of the high-speed oil flushing is to clean the system, to clean the metal, remove any strange particles inside of the lubrication or the hydraulic system. But sometimes we also purify the oil, but that depends on the procedure, so don't confuse. The high-speed oil flushing is to clean the system, the metal, not the oil.
High velocity oil flushing. In this technique, the unwanted particles in a lubrication or power oil systems are removed using a turbulent or high velocity oil flow and then captured in a filter. In this animation, we see the internal surface of a pipe. Then we have the external particles, all that debris that is left behind during the construction of the pipes. And finally, with a high-speed flush, we will remove and drag all those particles that then finally will be captured in a filter.
The purpose of a high-speed flushing is to keep the particles suspended and avoid that they settle down. More speed means more turbulence, and more turbulence will facilitate the suspension of the particles like we can see in this animation. Boundary layer. Boundary layer is a layer of the fluid that has almost no velocity or zero velocity. Turbulent flow is like rapids. The main stream will move fast and chaotic, but close to the river edge, the velocity is slow and eventually zero. We can see here in this picture how the main stream is very fast and turbulent. But when we get closer to the edge, the river edge, the velocity is diminished and eventually it's zero. Boundary layer in pipes. Like the rapids, the flow inside of a pipe will have a microscopic layer with no flow stuck to the pipe wall and a free stream moving quickly. If a microscopic particle reaches the boundary layer, it will settle on the bottom of the pipe. In a horizontal pipe, the particles will settle along the pipe. But in a vertical pipe, the particles only will settle on the lowest part of the piping.
But if the particles are going to settle anyway, what should I do? And the answer is pretty simple. Keep flushing. It's just a matter of time. If you have more flow, that means more velocity. That means more turbulence and eventually faster and better results. In this animation, we see how that red particle is moved or dragged away faster if the flow is higher. That's a slow flow. Then we go faster. And then faster. And it's just a matter of time. In this chart, I have specified the minimum flow and velocity requirements to achieve a turbulent flow. Of course, higher means better. In the very first column, you have the pipe diameter for a Schedule 40 pipe. This is the velocity in feet per second. If you are more familiar with the metric system, this is the velocity in meters per second. Then you have the flow in gallons per minute, and the last column is the flow in cubic meters per hour. And of course, you always need to consider what is the liquid that you are pumping. This chart was generated using the properties of the turboflow RNO32, which is a very common lubricant for turbines in Canada. And the temperature is 70 degrees Celsius, which is also a typical temperature for a high-speed oil flushing.
So far you have learned that in order to clean a lubricant or a hydraulic system, basically you need to pump as much oil as possible, and that's easy, isn't it? But that's not the case. Here I will give you 12 recommendations to improve your oil flushing, and you will discover that the devil is in the detail. Number 1. Consider your needs for oil flushing in the design stage. For example, if we have a turbine, And the lubrication pipes will look something like this, where we have an oil tank or reservoir, pumps that will suck the oil from the tank and filter it, and then pump into the bearings in the turbine or the gear reducer or the drive, and then all that oil will be collected in a common manifold and then returned again to the oil reservoir. And our procedures or the manufacturer recommends to install a filter here just at the return before the oil reservoir, and that pipe is big and heavy and there is no room to install a filter there, we better consider that from the very beginning. And then we installed a pipe spool there. In that way, it will be very easy to install a strainer or to install a filter during our oil flushing.